We are going to talk about vitamins today. Vitamins come from the two words, vital amines. Vital amines. Vital means important, and amines containing the nitrogenous group. And they were called vital amines because they are very much important for health, because whenever there is a deficiency, it would lead to certain disease. And there are two types. One is water soluble and the other is fat soluble vitamins. They are water soluble and they are fat soluble, meaning that they are present in lipids. One, they are present in lipids. Second, they may be stored. And third, they may run the risk of toxicity. Yes, water soluble are, they are usually not stored. Usually they are not stored. So, and then there is a lesser toxicity. And excess may be excreted in urine. So they are less toxic. So that's why they call it water soluble and fat soluble. Well, there is another point in it, that lipids contain these fat soluble vitamins. So if there is any disease affecting the absorption of lipids, will definitely, if there is no absorption, this will cause a deficiency of fat soluble vitamins as such. Now, the fat soluble vitamins they are of four types: vitamin A, vitamin D, vitamin E, and vitamin K. While the water soluble are all B complex vitamins, all B complex plus vitamin C. So I repeat again, the fat soluble are four: vitamin A, vitamin D, vitamin E, and vitamin K, while the water soluble are B complex and vitamin C. This was for general introduction. Now, to start with, we'll start with water soluble vitamins. These water soluble vitamins, as I told you, they are, I'll write again, water soluble vitamins. These are B complex and vitamin C. All B complex vitamins and vitamin C. First of all, we'll pick up a B complex vitamin. Then we'll talk about vitamin C. B complex vitamin, there are so many. I'm going to talk about B complex vitamins. They are thymine, riboflavin, niacin, pantothenic acid, vitamin, then it is pyridoxine, then it is biotin, well, then it is folic acid, and vitamin B12. So I repeat, the important ones are, this is the B complex vitamin group. The important ones are thymine, riboflavin, niacin, pantothenic acid, pyridoxine, biotin, folic acid, and B12. Thymine is also called as vitamin B1. B1. Riboflavin is called as B2. Niacin is called as B3. Pantothenic, well, it is B5. Pyridoxine is B6. Biotin is B7. Folic acid is B9. And B12 is B12, cyanocobalamin. Though they are all very important, and they will be talked in this manner or whatever, but I would like to pick up the last two first. Although all these are important for both males and females, but one vitamin has got a greater importance in females, and especially so in women, and especially so in women of childbearing age. That means, just to highlight, I've given it a bit of priority because this is most important to be given to the ladies during pregnancy, and that is called folic acid. Folic acid. That is vitamin B9. Now, folic acid comes from the word foliage. Foliage. That is, the source is plants. Plants. Green leaves. Chemically, this is made up of three molecules, three compounds. One is pyridine plus para-aminobenzoic acid plus glutamic acid. So this is pyridine. Then you've got para-aminobenzoic acid. And then you've got glutamic acid, third one. So these two get together to form T-royal glutamate. T-royal glutamate. steroid glutamate. This is called folic acid. Now I must tell you one thing, that this folic acid is essential to be taken in the diet, especially for females and of childbearing age. The dosage is 300 to 400 micrograms per day. 300 to 400 micrograms per day. This is important. This is very important because if there is folic acid deficiency, the pregnant woman will get two problems. One is anencephaly and the other is spina bifida. Well, these are developmental anomalies of the fetus. Anomaly of the developing fetus. That is, there is brain defect and there is a brain defect. Brain defect, and second is there is a spinal cord defect. In addition to plus megaloblastic anemia. Megaloblastic anemia. That is, the cells are bigger than the normal. The RBC's diameter is greater than 7 micrometer RBC diameter. So this is important. Hence, for every woman, especially of childbearing age, it is important to give her folic acid, and the dosage is 400 micrograms per day, may be given empirically. Now, why is it so? And I will tell you the reasons for it. Folic acid, that is steroid glutamic acid, is involved in one carbon metabolism. It is involved in one carbon metabolism. That means the one carbon compounds, for example, this one is methyl. This one is methylene. This one is methinyl. This one is formyl, and this one is for amino group. This one is formyl. This one is for amino group. This is all one carbon. You can see that they're all one carbon compound. This is methyl, it's got one valency available. This is methylene, it has got valency on this side and combined with this side as well. Then this is called methinyl, CH. This is methinyl. So methyl, methylene, methinyl. This one is formyl, MYL, and this is form amino group. So these are all one carbon compounds. That is, they are all, it can add one carbon compounds. The biochemical role is, this is its biochemical role. Of B9 folic acid that carries out one carbon metabolism, and these are all one carbon groups: methyl, methylene, methinyl, formyl, and form amino group. They are all one carbon compounds, and folic acid carries these compounds. Folic acid carries all these compounds, attaches them, and so carries on essential metabolism. What essential metabolism? The essential metabolism is that it forms DNA. That it forms DNA. DNA. How? DNA contains two things. They could contain two types of bases. One, purines, and the other pyrimidines. Purines are adenine, guanine. Adenine, guanine. And pyrimidines are cytosine, uracil, and thymine. Purines have this structure. While the pyrimidines have got this structure. These are purines and these are pyrimidines. In purines you have got nitrogenous bases over here. This is the nitrogenous base. And then you've got a nitrogenous base over here. In pyrimidines, similarly you've got a nitrogenous base over here and a nitrogenous base over here. Rest is all methyl groups. This is all carbon. Rest is all carbon. Sorry. This rest is all carbon. These are all carbons. This is the carbon, right? So this is the structure of purines and pyrimidines. Now I told you that folic acid forms DNA. How it forms DNA? That it forms both purines, it forms both purines as well as pyrimidines. How? This is carbon number 3. Carbon number 3. This is carbon number 3. It forms carbon number 3 by the addition of formyl group. Formyl group. It attaches this carbon formyl group over here in the form of formyl tetrahydrofolate. So it attaches over here, while it forms this carbon number 8. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Carbon number 8 by means of methynyl tetrahydrofolate. Methynyl tetrahydrofolate. I would again tell you that this purine needs the formation to be, purine is essential for the formation of DNA. Pyrimidine is also essential for DNA formation. So, and for the formation of purines, well, this is the structure of purine. So, there should be a carbon at carbon number 3, and there should be another carbon at carbon number 8. So, the carbon number 3 is formed by folic acid by providing formyl group, and carbon number 8 is provided, this carbon is provided by, again by folic acid, by forming methynyl tetrahydrofolate. Similarly, on this side, it has an importance in the formation of pyrimidines, especially so thymine. Now, this is the structure of uracil. For it to be converted into thymine, you must have a methyl group over here. Methyl group, CH3. This methyl group is provided by methylene. Methylene tetrahydrofolate. This folic acid will take methylene group, and via methylene group it will provide carbon at this compound, thereby converting it into thymine. Thymine. So, well, when a DNA, contains adenine attached to thymine, and it also contains guanine attached to cytosine. So for DNA you must have adenine and guanine. Well, when the purine structure is formed, you get the formation of adenine and guanine, and when talking about pyrimidines, it helps in the formation of thymine. So it forms this, and this. If thymine is not there, again DNA will not be formed. So, what is the importance of folic acid? It helps in the formation of DNA. Very simple, so very important. And especially so in the females, and especially so in the development of fetus. I have started with this one just to emphasize that the importance of folic acid in the diet is very important. And for all childbearing age females especially. And so they must take it as a routine. About 400 micrograms per day is not going to cause any toxicity whatsoever. But mind you, the deficiency would lead to catastrophic problems during pregnancy or whatever, and will also lead to megaloblastic anemia. So, just to emphasize this. Now, bit of absorption and the procedure and little more points in it. I told you that folic acid must be taken in diet to carry what? 1 carbon metabolism. Now, if 1 carbon metabolism has to be done, folic acid must be present in the diet. And in the diet, it is present in which form? Tear oil, that is pteridine, plus folic acid, plus glutamate. In the diet, it is present in plants, foliage. And while taken in the diet, it has got a tail of 7 glutamate residues. So, this is folic acid. It is taken in the GIT and it enters the intestinal cell, in the ileum or wherever. It enters over here, and here it is ripped off the glutamates, the glutamate tail is shortened, and then it enters the liver via blood. So, in the liver there is pentaglutamate. It enters in the liver, and from the liver it enters into the blood as monoglutamate. Monoglutamate residue. Monoglutamate. And monoglutamate folic acid is now present in the blood, in the liver. From the monoglutamate, I will tell you that it is now in the form of, simple if I write it down, it is folic acid. This is monoglutamate. In the liver. Now, this monoglutamate carries what? 1 carbon metabolism. But before that, it has to be activated. It has to be activated to tetrahydrofolate. First it will be converted into dihydrofolate, then it has to be converted into tetrahydrofolate. Tetrahydrofolate, dihydrofolate, and this is tetrahydrofolate. This is the active form for one carbon metabolism for the formation of DNA and all the tissues there one. And the enzymes involved are dihydrofolate reductase. Again you have got dihydrofolate reductase. This is the enzyme involved in these two steps. So folate has to be activated, and once when it is activated, then it will carry on this one carbon metabolism, and then it will form the DNA and everything will be alright. So if there is folic acid deficiency, no active form, no formation of DNA. Or if there is, so if there is deficiency of this A, then again there will be no formation of DNA. Or if there is deficiency of dihydrofolate reductase at this level or this level, again there will be deficiency in the formation of DNA. And there is one more thing. Third is that if there is no or deficiency of vitamin B12, this is B, dihydrofolate, and C, vitamin B12 deficiency, again there will be deficiency of DNA formation. How? Because the moment tetrahydrofolate is formed, it is trapped